Okay, welcome back, everybody. I wanted just to use the first 4 or 5 minutes to give you a quick reminder from last week about practicalities, technicalities, and so on, because we have some new people and who may not be familiar to both the setup at the university here and also basically where you retrieve the information. And then I wanted to say something about the plan for the day and a little bit more about where we have information about projects, etc., etc. So today, I mean, we are going to look more into something which many of you have seen before, but it can be useful as a way to refresh when you bring back to life your neural network code. And if you haven't written one, hopefully this kind of quick review, which we started with last week, which I actually wanted to try to complete today, this will kind of a way serve to remind ourselves about how we can write a neural network code. Now, neural networks, as we said last time, they're actually the kind of basic method. You can almost think of as like a kitchen item, which enters many of the more advanced methods. If you're dealing with autoencoders, you will see that you may end using a neural network. If you're dealing with transformers, it's the same, etc., etc. So having understood how you write a neural network code is actually central for understanding many of the other methods which we will deal with. And clearly, to have a critical view on what are the possibilities and what it means is also very important. Then, as we said last week, I mean, one of the tasks was actually to bring back to life, if you have one, your neural network code, and just look it over and remind yourself about technicalities. And then the other task was to start thinking about the projects. So after the lecture, we will actually have a discussion. So some people have already uploaded the projects they want to discuss and present, data sets they have, and the possibilities to analyze these with the methods. Because this is the lab session is a very, very low-key session. And gradually, as you develop these project ideas, we can put them under a folder, which I will show you where you find. And then you can look up what people have been suggesting. If you don't want to put it there, I mean, it would be nice anyway to have a presentation. So we will use this lab session after the lecture and also the next one to try to finalize project ideas. I will also, by the end of this week, I will upload different project proposals. Then you can look at them if you say you're in doubt what you want to do. Okay? So the basic information which you have is obviously, or the links to the information is actually the standard UIO website. And for those of you not familiar who may have arrived recently, you can actually subscribe to these services. So with eventual updates about change of lectures or whatever happens, or when I typically after the lecture, I upload a video of the lecture, which means that you can always find that one under the schedule. And as I said last time, the plans you see here for the week are also in the emails which you get on a weekly basis about an update and plans for what we want to do. And you will also find it on the Canvas. So actually 3 channels from where you will get the same type of information. So it's information overloading. Hope you survive that. Now, the other main site is actually this GitHub site, where you find the essential information with lecture notes, program examples, Jupyter notebooks, etc., etc. And there's a schedule here which I keep updating, which is also reflected in the official schedule on the official website. And you will immediately after the lectures, you will find the videos and the whiteboard notes, etc. So you can always revisit things. And if you go into this doc folder, if you look into that one, then you will find under projects here, and in 2000 there's a 2026 project proposal one, and there are project examples from previous years which you can look into just to get inspired and see what happens and what people have done. Here we have 2 proposals. And not everybody will be able to be here. So for some of them, you can actually look them up and see if there is something which you're interested in, and then just contact that person and say that, hey, your topic is very interesting. Would you like to collaborate? And so on. So we normally recommend to team up with 2 to 3 people. That is often very beneficial, and it's a very nice way of sharing the load. And also, if you have the possibility to have complementary competences and knowledge, that's even better. Somebody may be good in mathematics, some in coding, some may be very good on a specific discipline, etc., etc. Then, if you just move down here or along this folder, you will also find literature. There's a whole set of deep learning books, which I've added there. And many of these are textbooks which you can access for free from the university library. And then if you're interested in numerical optimization, so this is something I mentioned last time. Last year and the year before, we had people who were interested in the optimization part of machine learning methods. So that's a field by itself in mathematics. So if this is something which is also interesting, you can also define a project along those lines, for those of you who may be more mathematically interested. And there's actually a pretty good textbook, which is called Numerical Optimization here, which you can download. So the textbooks which I put here are normally textbooks where the authors have given up copyright because they've seen so many people distributing pirate copies of their textbooks. So the reinforcement learning by Sutton and Barter, which is one of the standard textbooks, is available from their website. So, and the Springer textbooks, which you will find, are textbooks which you can also get from you going to the university library with your UIO identity. And then you can download all these textbooks for free. So essentially all publishers, they provide you with access to PDFs or a collection of the chapters. So sometimes you would have to download individual PDFs and then bring them together into textbook. But this is normally the big publishers like Springer, Cambridge, Oxford, etc. Since the university library buys these services, then you have access to the textbooks. So you don't need to buy the textbooks because some of them are pretty expensive. They are typically in the order of hundreds of euros. Okay. Any questions about the practicalities? Okay, so I wanted to switch over to the slides for this week. So I'm going to switch between slides and the whiteboard. And we're also going to do some Jupyter Notebook. So when I typically run codes, I will always use a Jupyter Notebook. And so let's switch to the notes here. And then I wanted to bring back to life some of the technicalities with neural networks, which we started to look at last week. So the basic, there are some basic informations here. And I also mentioned to you that since every year there's somebody who's more interested in the mathematics of deep learning, there are actually 2 excellent textbooks which you can download. And that could also provide the basis for a project path. So as I said, optimization, the mathematics of deep learning is something which is also a topic which can be interesting for many of you. So we try to keep this kind of flexibility in the definition of the projects. I'm just going to skip this because this is just the repeat from last week. And also last week we discussed the setup of a neural network. I'm coming back to this. I just wanted to remind you quickly of the things which I'm going to do now, but I'm going to bring up a simpler version of it. So the neural network essentially contains a model, or is described by a model, which is the architecture of the network, and that has an input and output layer. There's a given number of hidden layers. You have activation functions, which we are going to remind you a little bit about. There's a whole series of activation functions which are being used for, let's say, transformers, and that they are members of what's called the GLO family. Some of you have been using the ReLO, then you have the ELO, but then you have new activation functions which we will come back to. So there's a whole plethora of activation functions. And they are part of what we would call the architecture or the model itself. And then we have the last layer, which is normally called the output layer. And that may have specific activation functions tailored to the problem you're looking at. And then you have a cost function, which you typically end up defining. So that's just a quick reminder. And what we are going to do is actually to look at an optimization problem of a simpler type, a regression type. And the reason for why I bring up the mean squared error, which is the typical way you would see that from a linear regression case, where you have a linear dependence with the input variables and the unknown parameters. And then you take the gradient of this quantity in order to optimize and find the optimal values for the parameters theta. But we are going to use a kind of mean squared error in the examples which I go through on the whiteboard now, just to remind people of the basics of a neural network and the kind of notations which I've been using in the codes and in the lecture notes. So this is just to bring back everybody to the same starting point. And for those of you who have this fresh in mind, because you have just recently coded a neural network, this may be a little bit boring, but I hope you can bear with me for that. The reason why I bring up the mean squared error as a function here is because that's the one I will focus a little bit more in the beginning of the lectures when we transit to the solution of differential equations. So today we are going to look at applications of neural networks to the solution of differential equations and what is called PINs, which is called physics-informed neural networks. And I will point to you where you will find the examples Jupyter notebook, so you can actually look them up and use them as a kind of template when you want to, if you want to use neural networks to solve differential equations. So this can define one project for the semester, or it can be a semester-long project, depending on how much you put into it. That depends on the scientific case you have. So as I said, I want to use the solution of differential equations as one type of applications of neural networks, in order also to bring up and remind you of the basic machinery. So for neural networks, these parameters are given by the so-called weights and biases to be defined below, which is coming up now pretty soon. So let me try to bring up a very simplified case. And we're going to switch to the whiteboard here and go through some of the really basic mathematics of a neural network. As I said, I hope you don't get offended if you see if you have seen these equations before. So what we are going to do now is to simply set up the simplest possible network. So instead of having a vector with data or a matrix with input data, we're just going to have a scalar in and a scalar out. Just one number in and one number out. And that is just to remind you of the basic notations which I'm using. So we are going to set up an example with no hidden layer. That's the first case. And this is mainly meant to remind you of the basic mathematical operations and how we actually set up the back propagation algorithm. And with that, how we update the gradients, which are then reflected in the equations for the parameters we want to update. So let's look at the basics. So this is something which many of you have seen before. So basics of neural networks or feed-forward neural networks. I will normally just shorten this to NN. So when you see this acronym NN, that is just a neural network. And it's normally just a feed-forward neural network. So the basic characters which enter into the game, this is the case with no hidden layer. And in this case, I'm also going to have a scalar in, x in, and the output, which I'm going to compare with, is also scalar. Y, which is the output, or what we normally would call also for the target value. So this could be some observation which you have. and we often call that the output or just the target value. That's pretty common names which are being used. So what we will have in this specific case, and normally you represent this graphically, so you would have an input layer, and in this case, we have only one input. But in general, if you're having, let's say, images, these images could be something like an image of 200 times 200 pixels. This is the way you store the information. That means you would have 40,000, 200 times 200 input values for every image. So that means you would transform that into a vector. And then if you have 1 million images, then you would obviously have this as a matrix, which stores all this information for you. And that, then the X which you see here would be a matrix which is fed in, which is then used for training. But now we're just going to just get up the basics and reboot your memories. We just wanted to go through some of these really simple cases so that you see the basic notation which we are using. So you have an input, and this feeds into some function. And we call this the, this is actually just going to be the final stage because there is no hidden layer. But in here, we are going to have some function, and I'm going to label that with a sigma 1. And this receives an input z1. Now, the input is modulated with some weight, which you call here. We are going to have a parameter which we call for a bias, b1. This is called a bias. This function here is normally the one which we call for the activation function. And these are different functions. So what we are doing here, you could think of us making a model for finding a functional dependence for the final variable which we are going to compare what the model gives us. Now, this function produces an output. And we're going to write it like that. And I'm going to call this for A1. This is something which you will often see also labeled as a Y tilde. So we would call this for the output or the output layer. In principle, the output layer is actually something which now consists of both these two here. That is the output layer where we have an activation function which then modulates the data we are feeding in. And then in here, we have a kind of model which is then supposed to give us an output. Now, this output is then fed into what we call a cost function or loss function. So this is our cost function, which we use to assess the quality of the model, because then this is then compared with the target value, which we call for Y. So this is our target, which we want to reproduce. Now, let's just look at something simple here, because you could think of this weight and this B as a model you have made to fit the data. And this data you're fitting could be represented by a first-order polynomial. So let me just give you an example of what this activation function could be like. So an example of this sigma 1 of z1 could be a simple function which is now given by w1 times the x value plus this b1. And this defines our z1. So the function sigma is just equal to this variable z. So that means that sigma is now us making a model which is a first-order polynomial, which is now going to be a model for the data. This is just to give you an example. That means that this activation function, which is a typical situation for the output layer, when you're fitting a continuous function, which is normally called a regression type problem, not a classification problem, that means that what you're doing now is that you're sending out via the activation function, the variable C without any modification. So that's very typical if you're trying to fit some function with a given neural network. So the last layer, the output layer, would then just be the output generated by the input Z to the specific output layer. So that means that there is no specific function here which changes the shape of or changes the output. So a typical activation function which you may be familiar with, the sigma 1, and then we just write it generically, that could be the sigmoid function. So which is an E of minus Z plus 1. That is a very standard activation function. And in the slides, we are going to list other examples, and we will come back to why this function is less popular for many type of simulations. But this will be a typical example, and then Z, in this case here, so C here, could actually be given by W1 times X plus B1. But then we are modulating it with a specific function. And just to remind you a little bit about the sigma function, the function, if you now plot it as a function of Z, and then you have minus infinity and plus infinity, and you have 0.5 here. This is a function which goes more like this, and then like this, and it flattens out. It's a little bit exaggerated, and you can see that my drawing skills are not optimal. It should actually have been more like this here, and then flattens out. Now, one of the problems with this type of activation function, because we are going to calculate gradients when we optimize the network, one of the problems is that this function here, you see, flattens out when Z goes to minus infinity and plus infinity. That means that if that function flattens out, its derivative is going to be pretty close to 0, and that causes problem in the training of a neural net. This is something we will come back to. Now, the other quantity which we didn't say anything about is this activation function. No, sorry, the cost function. So the cost function is something you would make, which then is something which reflects the type of data you have and also the insights you have about the data. So in this specific case, this cost function which we define will now be a function of Y, and also this Y tilde, which we call for A. And this Y tilde is now a function of the parameters of the network. So we could simply set this up as, in our case, this Y tilde is something which we call for A1, the output of the network. So in our case, we could simply say, since we have scalar variables, that this function is A1 minus Y squared. And in this case, we just have a data point. Normally, you would have 1 divided by the number of data points, because you calculate this as a mean squared expectation value. And then, in this case, we just have a scalar, and it's common to put a factor of a half, because when you take the derivatives, you get rid of the number 2. You don't need to have it. Normally, when I use the mean squared error, I have 1 divided by n, the data points, and then the sum of the differences between the outputs of the model and the target values. So the more general formula, which many of you have seen, is something which goes like 1 divided by the number of data sets of I equals 0 up to n minus 1. And then you have a Y of I minus this Y of I tilde, which is the output of the model squared. And this is normally called what we call the mean squared error. So this is the function I will use in this example when we are going to set up the equations for a neural network. So we just have a scalar network here. And what we are going to do then, if you now look at the model which we set up, so we have a function C, which is going to assess the quality of the model, and we can write that one out as 1/2. And then I have a sigma 1 of Z1. So it doesn't matter whether we interchange these because it's just squared. And then, and here we would have a simple model for that, W1, which is W1, which is one of the parameters, plus B1, and which is called the bias. And this is often introduced in order to avoid that by accident the weight is zero, because then the output would be zero. So you normally have a offset when you initialize a network, so in order to avoid zeros being propagated. So in our case, what we have is two parameters of the network, and these are the parameters W1 and B1. And these are the parameters we want to optimize with respect to. So if we then look at the optimization problem, which we are going to do, so we are going then to optimize DC with respect to W1, and we want to drive that one to zero. And we also want DC of DB1, and we want to drive that one to zero. Now, if you look at the equation which we have, you will then see that this DC, and this is basically the chain rule. So backpropagation, the algorithm, is just a repeated usage of the chain rule. So if you look at your input, it does not depend directly on W1, because A here is a function of W1 via the activation function. So that means that we need to use the chain rule to find the derivatives. And I hope, again, you don't get offended if I just remind you of these things. So we have a DC with respect to A1, and then we would have a DA1 with respect to DC1. So this is just an applied application of repeated application of the chain rule. Now, this function which you see here is nothing but the derivative of this activation function. So if you look back at the equations we had, this variable A1 is now given by the output. So if you look at this function here we just assume that this was equal to Z1 in case we're dealing with a regression problem. But in general, what you will have is that this one is actually equal to this variable A1, the output of the network. So that means that when we take and use the chain rule, then we get the derivative of A1 with respect to Z, and that gives us this derivative which you see here. And then we have the final one where we have the derivative with respect to W1, and that's the one which we can compute from the explicit assumption we've made about the network. So then we have, based on the parameters, we have a possibility to calculate that derivative. And this derivative is nothing but A1 minus Y, the target value, times sigma 1 derivative multiplied with X, which is what we have here. And you can see that because Z1 is given by W1 times X plus B1. So that's the first derivative. And everything gets complicated when you have vectors and matrices. We have more than just one data point in and one data point out. But the basic philosophy is the one which you see in these equations. And then in the slides, you will find the generalization of this to multi-inputs and multi-outputs and many hidden layers. But this is just to remind you quickly of the basic operations which we need to do. So if we then move on, we need also the other derivative. And the other derivative which we need is DC, the cost function with respect to B1. And in this case, this is just going to be DC, DA1, and DA1, DC1, again, the chain rule. And when you deal with matrices, you will need the derivative of matrices, etc., etc. Now, this quantity here is often brought together into one variable, which you in the literature will often see called for delta. So this is calculated at the end point, the output. So this is something you would start the calculations with. And then this quantity here is just equal to 1. So that means that this DC dB1 is actually equal to this variable delta 1. And then if we go back and look at DC dw1, then what we have is dc, just let me repeat that one on this page here, which is this delta 1 multiplied with x, which is a derivative. So just to remind you quickly, dc1 of dw1. So we would typically write this one as delta 1 times x. Now, what we are doing then, when we have the derivatives by the chain rule, this is actually the basics building element in the backpropagation algorithm. When we have that, then we can implement our favorite optimization method for the gradients. So, and that gives us the next step, which is the training of gradients. And this is how we update the unknown parameters. So typically in the beginning, we would initialize these variables with some random choices. And these parameters get now updated with the previous value, W1, minus, and then we have a parameter eta, and then we have dc W1, which is the same in our case as this delta 1 times x. So we have the expressions, and then the thing we need to do is to plug it in our favorite optimization algorithm. So this is also something which we will discuss in more detail a little bit later. But the parameter eta, which you see here, is a parameter in the literature and also in actual applications, because when you use Newton's method, which is the starting point for calculating the update of the parameters. So it's a Newton-Raphson algorithm, which is the basis. But the problem then is that you need to invert a matrix when you have many variables, which represents the second derivative of the cost function with respect to the constant, with the variables. So if you have 1 million weights in your deep network, it means that the second derivative will be represented by a matrix, which is a 1 million times 1 million. And you have to invert that, and you don't want to do that. So numerically, it's much cheaper to explore different values of this so-called learning parameter eta. So you would set up a grid of variables, and you would then use the variables which give you the best possible mean squared error. So this parameter which you see here, if we now just bring everything up here, so B1 would then be updated iteratively in the same way. But in our case now, the DC of dB1 is nothing but this parameter delta 1. Now, this quantity here is what we normally call the learning rate. And there are many ways to update that, and many of you have written codes for doing so. The standard method, which is used widely in essentially all implementations, is something which is called the Adam optimizer, where you bake in information about the gradients and you optimize or update iteratively the value eta. You can also run it with a fixed one, and then you would have what we normally call the plain brute force gradient descent method. The alternative which to plain gradient descent is to use stochastic gradient descent, which is one of the methods which you will implement. And these are options when you use PyTorch, TensorFlow, or any other library for the optimization part. But this is something then you will do many times. So the feed-forward algorithm then consists in the following. So if you now look at the network which we put up here, you would initialize the weights and the biases, and you just feed through X, and you obtain an output. Then you compare that to the target value. You calculate the gradients, and then you go backwards, and you update the weights and the biases. And that means that you have new values. That is one iteration. So one iteration is one update of the parameters. Then when you have updated the parameter, The next thing is to do a new feed forward. And then you go back and forth till eventually, if you look at the cost function which we have here, the ideal value is 0, right? You want to have 0 difference between your model and the target values. So that means you would perform this feed forward and back propagation steps many, many times till you have achieved the accuracy you are interested in, or which you think is acceptable. If you're doing a classification problem, a standard function which is then used is normally what we call the accuracy. And that is simply you counting the number of properly classified events and divide by the total number of events. So if you're happy with 80% correct classification, it means that you would predict correctly 80% of the cases. 80% is normally not that good. So many of the models, you would like to have them close to 100% and avoid overfitting, obviously. But you see, this is the basic mathematical recipe. And I've used this to introduce the algorithm. So the steps, when you look at the steps here, what you would have, if you now collect everything, there is one step, which is the feed forward. So you initialize the weights and the biases. And then you have the back propagation, which is you finding the derivative. So the back propagation algorithm is an algorithm which gives you the derivatives with a chain rule. So you have back propagation. These are just the expressions for the gradients. So I'm going to put delta of theta of C plus gradient descent. And gradient descent is the way you actually perform the update of the parameters. So what you have here, this step here, is one iteration or one step. And then you continue this iterative process till you have reached the convergence you are happy with. And if you have a mean squared error you're using as a way to assess the quality of the network, then you could say that if 10 to the minus 3 is acceptable as a mean squared error, then you would say, okay, I stop now. So that would be your stopping criteria. So what I'm going to do now is just to build on this model and make a simpler neural network with one hidden layer, but still a scalar input. And then you will see that the equations which we're going to plug in are the same equations, the basics of the equations, as those which you would have in the more general case when you have a input which contains many input variables and eventually many output variables. But if you have the basic mathematics from here, it's straightforward. So always be suspicious when somebody says straightforward. I wasted a whole week on that because I made an exercise in a course in quantum field theory where the textbook said it's straightforward to calculate that. And it was not straightforward. But this is pretty straightforward. So let's now have just one hidden layer, and then you see the basic operations which we are going to deal with. And after the break, we're just going to summarize and set up the general equations, which are those which we would implement numerically. So in this case, we are going to have one hidden layer. So we still have the input, x, just a scalar. And now we have a hidden layer here, which I'm going to mark in 2 steps. So the boxes are in my notation functions, and the circles represent outputs. So we have a sigma 1 of z1, same as before. This has a bias b1, and there is a weight w1 here. Now this first object you see here, everything which you have in here, this represents the first hidden layer. So we have only one node. So this is the node of the hidden layer, the only output. So it's a scalar output, but we can easily extend this to become a vector. We can have many nodes. And this is normally what happens when you set up a neural network. You would have many nodes in every hidden layer. So this is the first hidden layer. And in our case, this is the only hidden layer. So this is the whole hidden layer. Now this output which we have here, this feeds into the output layer. So this moves in to the output. So we have a new sigma 2 here, but now we have a variable Z2. And there's going to be a bias B2 and a weight W2. And this produces an output, which I'm just going to call A2. This goes into this function, which we use to gauge the quality of the model. And we feed in the target value. So we compare the target with the output. And the quantity which you see here then, this quantity here, this is now the output layer with the activation function. So this is now the output layer. And in this case, what we have is a set of parameters. So we have 4 parameters. So that means that we need to calculate 4 derivatives. So we have W1, B1. We have, so this is number 1. We have W2. And finally, we have B2 here. And in this specific case, the cost function is going to depend on the target values and this variable A2. And again, it's going to just be a function of a single variable of A2 minus Y squared. So then we need to start with the derivatives at the output layer. And then everything I'm going to set up now is just a repeated usage of the chain rule. So what we need now is simply to start with the derivative with respect to W2. And that is nothing but dc dA2, dA2, and then we have these input variables to the output layer. And then we have a dc2 of dW2 here. And again, we are going to call this one for a function delta 2. And this variable here is now, if we now look at Z2, since we're dealing with scalars, this is going to be W2 times the output from the hidden layer plus its weight B2. So that means that dC2 of dW2 is just equal to A1. And also we remind ourselves that this one is nothing but the derivative of this function C2, sigma 2. So that means that we have an expression for this quantity of W2, which is actually equal to this derivative of the cost function with respect to the output, the derivative of the activation functions. And that's when you see these expressions here, you see that the derivative of the activation function pops up in all expressions for the gradients. And that means that if the derivative of this function is close to 0, then the training will actually stop up for us. And that's a big problem. Alternatively, the gradients or the derivatives can explode, and that leads to the problem of exploding gradients. And there are ways to deal with both these types of problems. So the case of vanishing gradients, so how many of you did listen to Ben Joe when he gave a talk at the inauguration of the Trust Center? Yeah, some of you did that. So Ben Joe is actually one of what we normally call the founders of deep learning. And that's one of the textbooks we are using. And Ben Joe had a seminal paper in 2010 where they found the mathematical roots for the problem of vanishing gradients. And in a certain sense, many people claim that this is what really kicked off the deep learning revolution, because it had been a problem which had plagued neural network training for many, many years. People knew how to train them with the universal approximation theorem. You knew that this is a universal approximator, but then the training got stuck because the gradients were vanishing. And that was simply because the sigmoid function was the most popular activation function. And Ben Joe actually had a seminar paper in 2010 with the Gloro, and that really kicked off. I mean, many people claim that that really kicked off the practical implementations of many deep learning methods. Many of the methods have been around, like convolutional neural networks in the 1990s, etc. But the training really took off when you got rid of this problem here. So you see clearly that one of the roots of the problems is actually vanishing gradients due to the derivative of the cost function. And you see that in these expressions. Then, so this would be A times A1, and then it's pretty easy to see that dC of dB2 is just going to be given by this delta 2, because Z as a function of B2, when you take the derivative, just gives us 1. So that's the first derivatives which we need. And then we are going one step back, because now we have the derivatives at the endpoint, but we need also the derivatives here, because we have 2 more parameters. So we need a derivative for W1 and B1. And that's where the chain rule comes in. And this is essentially the basic elements of the back propagation algorithm. Us calculating the derivatives going backward. And when we have all derivatives, we set up the optators of gradients. And then we do the back propagation part, get new gradients, get new values for the parameters. And then we do a new feed forward pass. Then back and forth, and we are happy. So let me try to set up the next ones, and then we go for a break. So what we would need now, if we look at the function, so what we had is that the Z2 is given by, in our case, W2 times A1 plus B2. But you see also that this is equal to W2 times sigma 1 times Z1 plus B2. And in our case, this is going to be given by W2 times this function, sigma 1 of W1 times X plus B1 plus B2. So what we are going to do after the break is simply to calculate this quantity, W1. We need that based on these expressions. And we will also need of B1. And when we have that, then we have the gradient expressions, and we can simply set up the gradient descent and then update the parameters and then start the iterative machinery. I hope you don't get offended if I try to remind you of some of these basic steps, but this is the essence of a neural network without the complications of setting up matrices and vectors, because then you would have the gradients would then be derivatives of vectors and matrices. But that's where we use automatic differentiation, which saves our day, because then we can play around with many different activation functions without having to write down the analytic expressions. And that makes the project time much shorter, because project time is not only running the equations you set up or running the codes, it's also developing the codes. And if it takes a long time to set up derivatives, etc., that is the total project time, part of the project total time. So it's not only runtime, it's also the time you spend on developing the software. And that's why I actually recommend strongly using many of these modern tools like Claude and Anthropic, large language models, because they can shorten the time you spend on setting up the framework, and you can actually attack the interesting scientific problem you're after. As long as you know what you're doing. That's the. But I encourage people to use these tools. We can come back to that when we discuss the projects in more detail. Okay, so before the break, we just put up the equations for the derivatives at the endpoint, at the output layer. And now we need the derivatives at the hidden layer. And we are still dealing with this simple model where we have a scalar in and a scalar output from the hidden layer and a scalar output from the output layer. And when we are going to set up the general expressions, these outputs will in general be matrices of vectors, depending on the type of problem which we have. So if we now look at the expression for the first parameter, we can then just set up the chain rule again. So if we do the chain rule, we know that this will be dc of dA2, that's the endpoint. So if you look at the equations which we have above here, you see immediately that these are the expressions we need to think of when we are dealing with the chain rule. So then we would have a dc2, and then this is a derivative of dc1, because we know that the z2 here depends on z1. So that means we need this guy here. And when you're going to look at the general expression, you will see that this type of derivative pops up again and again when we are propagating backward, and we are setting up many hidden layers. So we would need that one. And then again, since we know that dc1 and with the final one is actually the derivative with respect to the parameter w1. Now, the equation which we have to pay a little bit attention to is actually the term here. And when I'm going to set up the general expression when we're propagating back, you will see that what we are getting here also applies to the general case. So here, this is an expression which we can obviously rewrite, because dc2 with respect to c1, we have to be a little bit careful, because that will depend, and then we use again the chain rule on dA1 and dA1 dc1. So if you look back at the expressions we have here, you will then see that when we break this down, we have to recur to the chain rule, and we have to deal with these parameters here. Now, this function here, the one we see here, this one is simply the derivative of the first activation function, the activation function of the hidden layer. And this dc2 dA1, if we now go to the expression which we have here, you see that this immediately translates into W2 here. Now, this term, which you see here, is the same which we had earlier, which we call for delta 2, this term. So that means that what we get now is a new term, delta 2. Now, the old term, delta 2, which pops up here. We have this intermediate term, which you see here, which now depends on the parameter W2, which we have from the output layer. So we have updated the value of that one with gradient descent. And then we are going backwards, and then we are going to find a derivative for W1, which then will depend on this parameter W2. We have the derivative of the new activation function. So again, what you're seeing here is that using the chain rule, you will get a repeated applications of derivatives of the activation functions. Because this guy here was a derivative of the activation function in the output layer. Now you have the derivative in the hidden layer. So if you have more hidden layers, you will see the derivatives of the activation functions popping up again and again and again. So a neural network is then, if you think of the chain of derivatives you're dealing with, if you have 10 hidden layers, there will be, with the scalars, there will be 10 derivatives of activation functions multiplied with each other. So clearly, the value of the activation function plays a crucial role, the way it looks like. And if you have vanishing gradients, this can really kill all the training. Because the training, so just to be a little bit careful when we say vanishing gradients, we want the activation, the cost function, like the mean squared error, to reach its magic value, which means 0. That's the ideal mean squared error. So you could say then, why don't we calculate the derivative of the cost function and drive that to 0? The problem is that you have all these nested derivatives, which are essential for driving the cost function to 0. But if you have one of the derivatives that derives it at the endpoint, the output layer, to be 0, that could be something which could happen by accident in the training. and then the other parameters would not be updated properly. So every step which we do does not need to imply that the derivative should be 0. So in our case, it's actually for the mean squared error, it's us testing the new mean squared error against the convergence criterion which we have set up. And if you know that you cannot reach ideally 0, you would put it to 10 to the minus 3, 10 to the minus 4, and then you will stop the iteration then when that has been reached. So if we now collect all these bits and pieces, because we have, if you also look at the last expression here, this one, and then we just go back to the expression for Z1. So Z1, which you see here, is the same as this one. So if I take the derivative there, this is just X. And since we're dealing with scalars, I'm going to call this for A0. So we often label the input layer as the 0th layer. That's a pretty common procedure here. So when we then collect everything, we get the derivative dc dw1 here, which is going to be given by this parameter delta 2 times sigma 1 times w2 times the output a0. Sorry, the input, which is x actually. This was x. And then it's common to just simply label this as a new parameter delta 1. So if you then take dc with respect to b1, which is the other one we want, then we know that the z1, which is equal to w1 plus x plus b1, then we know that the derivative of z1 with respect to b1 is equal to 1. And then the only thing which we are left with is actually this one. So in the general expression, you will then find these different deltas as the parameters which we need to update for every gradient which we are calculating. So when we now are setting up the final gradient descent, we have now the gradients for all the parameters. So we would have a w minus eta. Now you don't need to have the same so-called learning rate, but you can change that one. You can have an iterative one for all the derivatives, or you could just have a fixed global learning rate if you're just dealing with a plain gradient descent. And then we have a W1, which is being updated as a W1 minus eta. And this contains now delta 1 times A0. So you see a similarity here between all the expressions. So the backpropagation algorithm gives us all these parameters, delta 2, delta 1, etc. And the deeper the network, the more deltas you have. And then finally, you have in B1, which is updated according to this learning rate times delta 1. So A0 was the input, which we labeled as X, just a scalar in this case. So the complication when you're setting up a neural network with many inputs and a matrix which represents the weights is obviously that these expressions has to be converted into derivatives of matrices and vectors. That is the essential complication. But if you have this one, if you have this picture, you see easily that when you now add another hidden layer, you will just get new parameters and you will have updated expressions of these deltas, which are just defined by you using the chain rule for derivatives. So when I last week said in a kind of arrogant way that neural networks are just matrix vector multiplications plus the application of the chain rule, there is a little bit truth into it, except that the optimization part of the training is often the really difficult part and the one which can be problematic. And many of you know that. Any questions so far? So what I want to do now is just to go over to the just general expressions and remind you of those. And many of you have actually programmed these expressions. And then I want to jump into programs and the discussions of applications of this to the solution of differential equations. Because that's one of the paths which I know that many of you are going to do. And I will just use neural networks as a way to remind you. Differential equations as a way to remind you how to use neural networks. And we will also discuss this partly next week. And then after that, we are going to dive into convolutional neural networks, which is the next step. Okay, it's okay. So I'm going to switch back to the slides for a little bit, and then to the Jupyter notebook. So let me stop that one. So the more general network, now as you've seen the simpler case, this is just an example with 3 hidden layers. And you can have many, many different nodes. It's pretty common in the structure of a network that often you will run with the same activation functions for all the hidden layers, because else you get too many options to test. So the training gives you the update of the parameters, but the rest is fixed. So the number of nodes is fixed, the number of hidden layers is fixed, the activation function is fixed, the hyperparameters, which include, are fixed. That sets the architecture, but there are some of these variables which are not trained. So what is trained by the network are the parameters for the weights and the biases. These are the training parameters. And then the architecture itself is fixed. And then the next time you want to make changes, you could change the number of hidden layers, you could change the number of nodes in the hidden layers, etc., etc. So the typical procedure, which many of you are familiar with, is that you start with just one hidden layer, and then you have, let's say, 20, 30 hidden nodes. Then you do the training, and then you increase the depth of the network, either by increasing number of nodes, increasing number of layers. And if your results improve considerably, then you would say, hey, one hidden layer was not enough. And then you would go back and forth with many of these numerical experiments. So running a neural network is something you have to view as running a numerical experiment, period. And the network trains only the weights and the biases. The rest is fixed by you. And then a new network will have new layers, new hidden nodes, etc., and new activation functions. So typically the output layer, as we said, in the scalar case, it was very simple because we were just propagating scalars. But now you are propagating vectors and matrices, and the output could be a binary case. Then you would typically have just one output node, or just a function value with no activation function at the output, or you can have multiple cases here. So the case which everybody has met is this famous MNIST data, which is a set of handwritten numbers, roughly 60,000, and between 0 and 9. And then you want to recognize the numbers. That's a very famous training set. And I use that repeatedly in the lecture notes because it's a kind of benchmark. And it's easy to understand. That's the other thing. So what we end up doing then is actually to change, since now the weights, we don't have one weight, but we have a matrix of weights. And that means if you look at the equations, there will be a Z, a given node. This is the input to the node of a given layer L. And then you have the output from the previous layer, L minus 1. You have the bias for the specific node and the weights. So this is now the general expression for this variable Z, which we put up in these simpler examples. And then a typical activation function, which I have in the notes here, is the sigmoid. That's a very much used activation function. And in the examples here, you will simply see derivatives with respect to this function. But this is where automatic differentiation comes in, which I strongly recommend to use, which allows you to easily change from one function to the other one. And then these are the intermediate steps you need, which we also did when we run the calculation with a simpler case, except that now you have subscripts on all the variables, which refer either to a matrix or to a vector, and to the layers and the specific nodes. So this is read as connecting node I to node J in layer L from layer L-1. This is the output from that specific layer. And then we have the derivatives here, which are needed. So that means that this derivative here, which enters also in the cost function, has now the derivative of the activation function. This is a derivative of the sigmoid function. So some of these derivatives, there's always a balance you have to strike when you write codes. Because when you call automatic differentiation, even if that is a very fast algorithm, it requires some CPU cycles. If you can hard code the derivatives, then that can often save you some time, because if you have a network with 1 million parameters or 1 million nodes in total, you're going to calculate the activation function 1 million times. And then you're going to calculate derivatives of that 1 million times. So clearly, speed becomes an important issue here. And you all have access to the machine learning nodes of the University of Oslo. So I mentioned that last time, get an account on the ML nodes, just search for ML nodes, UIO, and then apply for an account. Because then you will get access to, it's not the latest graphic cards of NVIDIA, but it's still pretty useful. Runs faster than it would on your laptops, unless you have an extreme graphic cards on your laptop. That's also possible, and some people do have. So this is the case which we looked at with the activation function. So you see the output layer with this uppercase L has then these expressions here multiplied with the derivatives. And these derivatives here are those which we can calculate with respect to the activation function. So this is the sigmoid function derivative, the first term. And this is just the derivative of the variable dc and dw at the output layer. So that means that if we go back to the expression here, you will then see that for a specific combination of I and j, when you take the derivative of z with respect to this one, then you're left with this a here. And that is what you see here. So this is nothing but the generalization of the expressions which you saw for the simpler cases. And then you can compute all these quantities where you simply calculate the Hadamard product. That's element-wise multiplication. It's not a inner product or not a outer product. And let me just skip some of these ones. So what you also need to do then, when you have defined this one for the output layer, so this is essentially the expression, and it's a lookalike of what we had for the simpler case. And then we find also that for the variable b, it's simply given by this parameter here. And that allows you to set up the derivatives. And then when you have so this is the first step. So this will be the derivatives at the output layer, where you have defined this parameter delta, as we did in the simple case. So this just follows the same pattern, except that now you have multivariable functions. And then what you want next is the derivatives using the chain rule at a given hidden layer, L, lowercase l. And then what you do then is, if you remember that expression which we had, so I'm just going to go back again to the whiteboard just to remind you. So if you look at the expression here, where we are simply running over these different derivatives with respect to C, if you look at this term inside here, and we go back to the whiteboard, so let's just remind you of that. So at the whiteboard, what we did, and which is the analog case of what you saw there for the general case, is actually us taking this expression here. And then we can break this down in terms of this one times that one using the chain rule. And this is the same thing which we apply to the general case. So let's go back to the general case. So that means that what we need is actually, so this is actually something which mimics what we had before. And we need to calculate these expressions. So this is given by the derivatives in the layers starting from the output. So there's a layer after that specific layer we're looking at, not previously. And then we can, in order to calculate this one, we simply need to remind ourselves of these expressions. And then we can actually get an expression for this delta JL. And that's the final equation which we need. So look back at the simpler case and then compare the general case with that one. So I always recommend you, when you're rebooting your memory about neural networks, look at the simpler case and then look at the general case and just convince yourself that these equations are correct. Because when you're setting up the algorithm, then you set up the input data X, that's the first step you do, and the activations Z1 or the input layer, and compute the activation function and the outputs. You perform a feed forward till you reach the output layer, and then you compute all these Z values of the input layers, compute the activation functions and all the outputs which you need for all the layers. And then when you have that, you compute the derivatives at the output layer, and then you compute these derivatives or this parameter delta for all the other layers. You propagate back. And when you have that, then you set up the gradient descent. So the back propagation is an algorithm based on the chain rule, which gives you the derivatives. When you have the derivatives, you can set up your standard gradient descent. And the expressions, if you go to the specific case we did on the whiteboard, you will see that this mimics what you saw for the scalar case, except that now we have to be a little bit more careful because these are going to be to represent multivariable cases. But essentially what we end up doing layer by layer is to set up these equations. So the training of the network, if you go back then to the figure which we had, is essentially us starting with initial guesses for the biases and the weights. And then we input, we use the activation functions, and then we propagate through the network and then get the output. So that's the first feed forward pass. Then we calculate the derivatives here, the cost function, and then we go back, next derivatives, next derivatives, next derivatives, and update the parameters. And then we have new updates till we reach the last hidden layer. And then we have new values for the weights and the biases. And then we do a new feed forward pass back and forth till we are happy. That's essentially the algorithm here. Okay, so I just wanted to say some things about the, and I'm going to switch now to the Jupyter Notebook, because I wanted to, let me do that one. I also wanted to say something about the material which you may find of interest if you want to use physics-informed neural network. We will discuss this next week as well. If you go to this week's material and look at the Jupyter Notebook, there is a one file which is just the lecture notes which you've been seeing till now. There is a similar application in PyTorch from Rashka's book, which you have access to, if you want to look at that one. But then there is the template equation, which I'm going to use to introduce physics-informed neural networks, which is the Black-Scholes equation. But I will start with the diffusion equation as a differential equation. And in these files here, we are using PyTorch, which many people like as a library. So the recommendation here when we are setting up the codes is, unless you want to write your own code for a neural network and use your own code, try to use either PyTorch or TensorFlow. That increases, how to say, the productivity, in the sense that we have well-tested functions which run easily on GPUs and CPUs, etc. And the examples which you will find for the differential equation with pins is actually an example where we run with PyTorch. Now, in the lectures for this week, you will also find PyTorch and TensorFlow examples on how to actually set up your neural network code. So in here, you will find the basic things which I will discuss. So I will also go through the mathematics of how to solve the differential equations. And this will continue next week. So let's go back to the, I think this is the one I wanted. No, this is the other one. So this is the weekly slide. So let me just go down because there's something I wanted to say. So this is what we saw in on the PDF, but there are some things which I wanted to bring up to your attention. Are things which many of you have seen before, but I wanted to say a little bit about the activation functions. Can everybody in the back see well? Is it big enough? A little bit bigger fonts? A little bit. Let me just increase the fonts a little bit. Is that okay? Good, good. So one of the activation functions which many of you have met is the so-called Relo family of functions. This is just a constant. And then it has a small non-negative value when the input parameter z is less than 0. And this is a function which has been extremely popular. However, in many of the applications when it comes to differential equations, this is not the best option often. And many people actually use tanh. So the ELO is actually one type of activation function which many people have been using. But then, and I have to confess that when I've been solving quantum mechanical problems with neural networks, it's actually the JELO function which tends to give the best result. So there's a whole family of functions which are based on the Gaussian distribution. And this function here is often approximated like this. So it has a kind of tanh lookalike. It's computationally efficient and widely used in deep learning frameworks. One of the properties is a smooth and nonlinear activation function, weights inputs by their probability of being positive. And unlike Relo, negative inputs are suppressed smoothly rather than set to 0. It's empirically shown to improve performance in deep networks. Especially, I know that some of you are thinking of using transformers. So in transformer-based applications, this has been a very popular activation function. So keep in mind that for many of the applications, this is more you trying it, it works. Empirically, it gives better results than the other ones, but sometimes it can be difficult to understand why it works well. So when I've been using the JELO function, I've been having a problem where the quantum mechanical wave functions are actually harmonic oscillators. And that means that the activation function actually mimics the shape of the function I'm looking after. And then they have often given me better results than using Relo or sigmoid or tanh. But what typically many people do is that they try many different types of activation functions. So again, that is part of the architecture and where you will simply try different types of functions. So then it shouldn't come as a surprise that there is a whole family on you. And sometimes you don't see the wood for the trees because there's so many ones and you don't know which one to use. But there are some general recommendations. So if you go through the literature, you will see that like typically if you're dealing with transformers, there is a whole set of functions related to JELO. So you have some, I love these names here actually, Swish and Silu and Mish. And so you see there's room actually for you coming up with your own function with its fancy name here. So some of these are quite popular ones, like if you're dealing with transformed-oriented wave activation functions, there is a whole set of it. I'm just listing them here because I have not tested these. So I've been testing JELO and ELO and ReLO and all these family of functions. And the JELO ones are the ones which often have worked best in my applications to physics-informed neural networks. That's from my experience. So which activation function should you use? In general, it seems that this JELO or ELO activation or the whole family there are better than the leaky ReLO. So the leaky ReLO is a function which has small values when z is negative. The ReLO just has no values when C is negative. It's just a continuous first linear function in Z. So ReLU often performs better than tanh, which in turn often performs better than the logistic one. But everything you're going to do is a numerical experiment. So that's important to keep in mind. So there is also a little bit more here, which kind of activation functions. There are tricks like batch normalization. So the textbook by Goodfellow, Benjo, and Colville has a chapter 11 and 12, which I normally recommend to take a look at because they have collected many of these kind of practical tips and hints on training of neural networks, convolutional neural networks, and recurrent neural networks. So I will not go through all these details, and I would just refer to the textbook there because that contains a pretty good, actually, description. And there's more text here, which I just simply recommend to take a look at. There are some limitations, obviously. You're often using labeled data. These statements should be not taken too literally, because when you're solving differential equations, then a neural network is actually a generative method because you generate a solution. And then you don't need labeled data. So even if you will see statements like this, I'm just bringing this up because it's not fully true. So neural networks can actually be used as generative methods. So normally all these supervised learning methods, they often require labeled data. And labeled data is something which can be limited. And they are normally very data intensive. So clearly, the more you have, the more data you have, the better the fitting. But that's common for basically all statistical analysis data methods, machine learning methods, etc. It also works best normally on homogeneous data. And what I wanted to say a little bit about is the code example. So this is something which you had as a homework last time, where we wanted you to bring back your codes. We do have a code example here, which was developed by actually 2 students who took this course. And they developed a convolutional neural network code based on this neural network code. That was their project. And this is an example of how we build up all the different elements. But if you want to scroll down, and this is what I'm going to do now, I'm going to bring you down to the TensorFlow example and the PyTorch example, because that's the kind of software which many of you will be using. And we recommend using that one. So I'm going to skip many of these, but we have at the bottom of the slides, we have PyTorch examples, and we have a TensorFlow example. So the typical, so this uploads the MNIST data set, the full MNIST data set. And then here, you're defining a neural network with, so the input is actually a 28 times 28 image. And then we have a hidden layer here. So this is the input layer, which connects with the first hidden layer. So we have 100 nodes in the first hidden layer. And then we connect to a new hidden layer. So 100 weights times 100. So this is 10,000 parameters here you need to train. And then the final output, so that has 100 nodes from the last hidden layer, and then connects to 10 nodes in the output layer. And that's why you see 110. So this is the way you would typically set up the parameters of the network. So this is the input. So your images are images of 28 times 28 pixels. And then this image node, this input nodes connect to 100 hidden nodes. So this is the first hidden layer. Then you have the second one, and then you have the output layer. So it's pretty simple to set up the architecture here. And here we have loaded the data, which is also pretty simple to do. And then we have the feed forward part. So you see now that we are using the ReLU function as activation function. So we use that one for the hidden layers here. And then we are setting up a neural network. We are using something which is called the cross-entropy loss, which is the one we use now as cost function for the classification problem of a multi-class problem. And then we are using simply a stochastic gradient descent. So in this case, the learning rate is fixed. And then we have a weight decay, which is also used in the stochastic gradient model. So this is just a plain stochastic gradient. And you can improve that one by adding Adams, optimizer, root mean square propagation, etc., etc. So I know that many of you have already used this. And then we are setting up the back propagation part. And essentially, this is the basic things you need to plug in order to get started with PyTorch. If you're using TensorFlow, it's also pretty similar. TensorFlow is Google's answer to Metas. And again, you see here, you define the layers. So here you define the activation function. You can define the type of hyperparameters. And this is an L2 norm parameters. So these are additional parameters. And then you define the final layer. So these are the two hidden layers, as you can see. This is the input shape, 28 times 28. So the notation is a little bit different. But if you take an overarching view, you see essentially the same type of ways of setting up the networks. But you have just different function calls. So this is done with Keras. And then you have the activation function, which is a softmax. You call the optimizer, you have a learning rate. These are the same set of parameters. And then you train the model. And then you have this also contains some validation, which we are coming back to. The number of epochs, batch sizes, etc. These are parameters which are fixed when you train. And then typically you would change these parameters. So keep in mind that the training, it's only update of weights and biases. These are your parameters. The rest are also parameters, but they're not trained. It's you who have to fix them before the training. And then new parameters, except for the weights and the biases, represent a new network which you train and a new experiment. Basically, these are the things which you end up doing. Now, what I wanted to bring up here, and this is something we will continue with next week, is the solution of partial differential equations. And actually, this was a project by Frederick, Oscar, and Christian last year. And they were interested in solving the Black-Scholes equation, but we will start with the diffusion equation. The Black-Scholes equation is a diffusion equation with a stochastic term added. So solving the diffusion equation, so for those of you who want to do physics-informed neural networks and diffusion and partial differential equations with neural networks, what I typically would recommend is to start with a case where you have a simple equation, like the diffusion equation in one dimension and plus time, and then find a case where you have an analytic solution, where you know the answer, and then you set up the machinery. So some of you have done this in FYS5429, but the idea here now is actually to add the boundary conditions and the initial conditions, so to the optimization problem. So the difference between the kind of brute force approach, which many of you did in FYS415 was that you tuned an initial guess on the function. So you tuned actually the neural network times some parameters, but now you're going to tune, in addition to the cost function, the initial conditions and the boundary conditions. So the cost function in this case, when you're solving differential equations, is actually you taking with a guess for the function. It's you taking the difference between the right-hand side and the left-hand side. So you start with a guess for you, which is your neural network. And that neural network can be guided with some insight from you. That's the physics-informed insight. Or you can just set up a neural network and not care about anything. That can often lead to serious convergence problems. So you typically guide it in some way. You take the difference between these two and you square the difference. So this is a mean squared error lookalike. And then you start with a guess for the neuron, for the wave function. You calculate this difference, you square it. Next iteration, you keep optimizing till the difference between the left-hand side and the right-hand side is as close to zero as possible. That's the essential, recipe seen from an overarching point of view. And this is what these codes are about. And next week, we will start with this, but feel free to take a look at it. And we will go into the Black-Scholes equation as a typical example of one of the differential equations. I know that many of you have interest in other differential equations, like the Navier-Stokes equation. You may be interested in wave equation type of problems. So this is something which these slides provide just the basic framework. And then it's up to you to take this basic framework and apply that to your problem. So next week, we are going to discuss that, and then we'll see how far we get and dive into convolutional neural networks. The thing which we do after the break now is that we will, for those of you who want to present the ideas for projects, we do that. I have received some already, so we can use a mix of the Blackboard or present with slides if you have them ready. So this is very much up to you guys. Some people have sent me project proposals, but they don't have the time, the possibility to be here. So then feel free to look up this folder with project proposals. So I would just suggest we take a short break and then people come back, and then we, for those of you who have thought of something, you can use either a whiteboard or present slides the way you want to do it. It's very low key. Huh?